Hello, hello, and welcome to the notes for 3.1. This chapter is very different from what we've been doing, and this particular section in this chapter is kind of different from some of the things that we're going to do in the rest of the chapter. This section is going to have one longer video and one shorter one. One of the things that we're going to learn in here, I'm going to do a little extra piece for at the end just so you have a handy reference. You'll understand why when we get there. But in the meantime, we're going to get started. So 3.1 is about numeration systems. We're talking about historical numeration systems and also things that we do today. What we use today is called the Hindu-Arabic numeration system, and it's based on place value, but we're also going to talk about Egyptian, Babylonian, Roman numerals, as well as our current system and how to convert things between bases, and that's the piece that gets a little tricky sometimes. Before we do that, though, let's talk about terms. In a system of numeration, a number is a quantity. It's an amount of something. You have a pile of things, it's a number of things in that pile. The numeral is the symbol you use to represent that number. 100, written out here, 100, is the numeral used to represent 100 things. C is the Roman numeral that represents 100 as well, 100 things. A system of numeration is the set of numerals along with the rules that you use for combining the numerals to actually show a number or a quantity, okay? So we're gonna work our way like from early to later, from simple to complex. The beginning of all of this really goes back to Egyptians. What we know about Egyptian math comes from this thing called the Rhind Papyrus, and you can actually go look at it. You can look at more information about it here at this link on the bottom, and it's old, right? A lot of the Egyptian civilization stuff it dates back, 5,000 years essentially. The Egyptian system is additive. So what happens is as you write the symbols out, it doesn't matter how you write them. Order is not in any way a part of how they added or how they wrote out numerals. It's not about the order. But what it is the symbols and the way symbols are used. So you can do addition and subtraction in an additive system, but other things are complicated. So let's look at the symbols. The Egyptian symbols are, fairly, complex and simple all at the same time. So a vertical staff, a straight line, is 1. This upside down U, a heel bone, is equal to 10. A little scroll, and mine are horrible, you'll see them in a minute, is equal to 100. A little lotus flower is 1,000. A pointy finger is 10,000. A little pollywog bug is 100,000, and a happy, yay, astonished man is worth 1,000,000, which is, about how somebody felt if you gave him 1,000,000 of anything. So how does this actually work? Well, we want to write, I'm missing a number. Where'd my number go? Hello, number. Sorry, let me look in my notes, see if I have the number, because I should. I don't know why it's not on my slide. Oh, I have to write the numeral. There we go. I have the numbers. So I'm going to draw you a number, and you're going to figure out what it is. Here is, so take a second, go back a slide, or rewind a little bit, look at this picture, and figure out what it stands for. Okay? So the scrolls are worth 100. It doesn't matter what order they are in. I know that I see 1, 2, 3 of them. So that means I have 300. Okay? The heel bones are worth 10, and I have 3 of those. That's 30. And then I have 2 vertical staffs, 2. So this numeral is worth 332. Let's try another one. Let me draw a different picture. So that's a flower. Okay. So now take a second, go back, Decide what this stands for. All right, well, I know the flower is worth 1,000. The heel bone is worth 10, and there's no hundreds. There's no scrolls in here, so I'm going to have no hundreds. The heel bone is worth 10. I have one of those. And I have one staff, so that's 1,011. Okay, so now we want to write the number 227 as an Egyptian numeral. Remember, order doesn't matter at all. So take a second, write your number. And I'll just be patient while we're doing that. All right, so any order you want to write this as in is fine. It's got to include 2 scrolls, 200, 2 heel bones for 20, and 7 vertical staffs. We are, like, our brains think in place value from left to right. So we tend to write our numbers in order this way. It's just the way our brains think. But if you did it the other way, and if maybe we went like this, you'll find kids will make patterns out of them. Still, same thing. 200s, 20, 7. Either is fine. So that is Egyptian. The next system is a place value system, which is like what we have today. The value of a numeral, of the symbol, depends on its position in the number. Where it is dictates what it's worth, right? A place value system requires a set of digits and requires some sort of base. We use base 10. Our system is a base 10 system. We move by powers of 10, right? That's our position. This is a decimal number system. DECI always stands for 10 of something, right? The Babylonian system was the first and oldest system we know about that was based on place value. It's, slightly younger than the Egyptian system. And its place value is a base of 60. So actually, it's very similar to what we think about today with angle measurement or with time, right? To a degree with time. There's 60 seconds in a minute. There's 60 minutes in a degree. You could also think of this as 1 hour, right? So they're counting in each thing. Each place value is 60. When you get to 60, you move to the next place value. Just like when we get to 10, we move to the next spot. So the place values are multiples of 60. So the first place value to the right, okay, if we think about places laid out like we would lay them out, right, is worth 1. Anything in here. Anything in this place value in the second position from the right is worth 60 to the first, which is the same thing as 60. Anything in the third from the right is worth 60 squared, which is 3,600. Sorry, that's a crazy 0. And anything in the third spot is 60 to the fourth spot from the right, 60 to the fourth, 60 to the third, which is 216,000. 216,000. And you could keep going, 60 to the fourth, 60 to the fifth, 60 to the sixth. The numerals in the system are a line for 1 and these little triangles for 10. When you write numerals in the system, what you do is you leave a space. So a Babylonian number would have some numerals and then a blank spot and some more numerals and a blank spot. That's how you determined that this was a group, and how many of each set of values you had. Okay, so let's try and see what that looks like. So I have, oh, sorry, before we do that, there is no 0 in Babylonian. So the space in between things tells us value, okay? And remember that our places, it was 1, 60, 3,600. So in this numeral, we have 2 places. This is 1 place, then there's a space, then there's another. And we always work from right to left when we're doing place value. So first we see what we have here. We have 10, 20, 21, 22, 23, 24. basically what that means is I have to do 24 times the value of that place, which is 1. So 24 times 1 is 24. In this spot, I have 10, 20. Well, I have to do that value times the value of the place, which is 60. 20 times 60 is 1,200. Now I add those two together. And this Babylonian numeral is worth 1,224 in our Hindu Arabic numbers. Weird, right? It's okay, we'll do it again. Let's try this one. So now think for a second. This has 1, 2, 3 places. So we need to think about what we need here. So I have 1, 2, 3. That's worth 1. Next place value was 60. Third was 3,600. Okay. So this first place value is 10, 11, 12. Okay, so I have 12 that are worth that first place value from the right, which is 1. Okay, and here in the next one, I have 10, 11, and they're worth 60. So I have 11 times 60. And then over here, all the way to the left, I have, let's use another color, 1, 2. And those are worth 300, or 3,600. 2 3,600s. All right, and now we just have to calculate, right? Well, 3,600 doubled is 7,200. Plus 11 times 60 is 660. Plus 12. 12 times 1 is 12. If you add all that up, I get 7,872. And that's the, 72. Yeah, that's right, sorry. That's the value of that Babylonian numeral, okay? All right, so the next system is Roman numerals, which you have seen and may or may not love. They are a little tricky, honestly, but they are still around today. You'll find them on buildings, you'll find them on the Super Bowl, you'll find them in all sorts of strange places where it would be useful to like sometimes know what they actually stood for. Excuse me. So you see them all over the place. The Roman system is additive, the Roman system is additive, but it's also positional. So it's not only addition, but the placement matters, okay? So first, these are the values of the Roman numerals, okay? These are something you need to know. So learn them, okay? Not like cheat sheet, learn them, learn them, learn them. So 1 is an I, a 5 is a V, an X is a 10. You probably know those. It's 50 and up that you may not know. L is a 50, C is 100, D is 500, M is 1,000. The other thing that you should be aware of, oh no, I think it's coming, never mind. Okay, so these are the numerals. In the Roman system, there is subtraction. So the way Roman numerals work, and you might know this, is that you begin from the left. Values are added unless the numeral to the left is smaller than the numeral to its right. If the numeral on the left is smaller than the unit on its right, it's subtracted. So if I had, for example, xi, it'd be 10 plus 1. X is bigger than I, right? That makes 11. But if the numeral on the left is smaller than the numeral to its right, ix, it means subtraction. 10 minus 1 is 9. Now, there's a really important rule here. You can only subtract numerals from the next 2 higher numbers. So what that means is that I could subtract an I from a V, an I from an X. That's it. Like I can't do 49 by IL. It's too far away. I can subtract V from an X, and V from an L, but I can't do VC. If they're more than 2 spots away, they don't work. You have to find another way. And then there are rules. So always start from the left and add each unless it's smaller. If it's smaller, it's subtracted. You can also only, oh, sorry, I gave you an example of the 5. We're not allowed to do that. You can only subtract powers of 10. I can't subtract the 5 or the 50, okay? I can't do VC like I just tried to do. Numbers can only be subtracted from the next 2 higher ones. The other rule is that a symbol can't be used more than 3 times in a row. If we write 40, we write it as XL, which is 10 less than 50, because we can't write 4 X's. And then the last thing is that if you have a bar over a group of symbols, that tells me that it's times 1,000. So if I had, let's say, XI, we know that's 9. If I, sorry, IX, I'm writing the right thing. My mouth is saying the wrong one. If I have IX, it's 9. If I have IX with a bar over it like that, it would be 9,000. And this actually compounds. So if I had IX with 2 bars over it, it'd be 9 million. Okay, 1,000 more than that. Oh, sorry. Okay, you can have as many bars as you want. That's how they got big numbers. All right, so we're going to talk before we do Roman numeral practice. We're going to talk about Hindu-Arabic. They are, so it comes from the Hindus in India originally, who began using 0, which is the big sort of forward movement in our system that other systems didn't have. And it's how they began to trade with other nations, particularly with the Arabs at that time. They traded, the Hindus used the system, they traded with the different Arab nations, and the Arab nations went like, oh, we're going to use this. So it's been around about, 400 or 500 years, so way young compared to Babylonian and Egyptian. But it's a system we all use now. Numerals are digits in our system. We have 0 through 9. And the positional values are powers of the base. Our base is 10. So ones, tens, hundreds, thousands, 10,000s. You know this. You've seen it before. When we write a number, we can write it in what they call expanded form. So if I have 7,634, I can think of it as 7 times 1,000 plus 6 times 100 plus 3 times 10 and 4 times 1. And I can write those numbers as powers of 10. 7 times 10 to the third, 6 times 10 to the second, 3 times 10 to the first, 4 times 10 to the 0. Remember, anything, a shoe to the 0 power is always 1. Okay? So then let's try this number in expanded form. Better yet, why don't you try it? Take a pause and come back. Okay. So think about how you say this number, 23,468. So I know it's going to be 2 times 10,000. And I tend to write my numbers like this first, plus 3 times 1,000, plus 4 times 100. And notice each digit has its own place here, right? Plus 6 times 10, plus 8 times 1. And I can now write these as exponents. So 2 times 10 to the fourth, plus 3 times 10 to the third, right? Powers of 10, we count by zeros, plus 4 times 10 squared, it's 100, plus 6 times 10 to the first, just plain old 10, plus 8 times 10 to the 0. Anything to the 0 power is 1. All right, so that's expanded form. Let's make some Roman numerals. So take a minute, pause really truly. Use the page of Roman numerals and the expanded form practice to go through and do this slide And then in a minute, we'll move on to the next one. But practice this first, because really, truly, the homework is going to be hard if you don't. All right, so I'm not going to write all the expanded forms in here because I just don't, the pen and the space and the, the whole thing. So we know this is going to be 7 times 10 plus, 10 to the first, and 6 times 10 to the 0. You can write those in, but I'm not going to do them all because you get the idea. I'm going to do 2 maybe. But let's do it as a Roman numeral. So think of each place separately. I want to think about 70, and I want to think of 6. How do I make 70? Well, I can make 70 out of 50 and 10 and 10. So L, X, X, 50, 60, 70. I didn't break any rules. And 6 is 5, 6. Okay. I should make my eyes right. There's 76. No big deal there. Everything's okay so far. 434 is 4 times 10 squared plus 3 times 10 to the first plus 4 times 10 to the 0. Now let's write it as a Roman numeral. Okay, so 400. How do I write 400? Here's the thing. I can't write, well, what's 100? Let's go back. Look at your chart. Remember, C is 100, but I can't write 1, 2, 3, 4 of them, right? That's not going to work. So what do I do? Well, I can write 100 less. Oh, I need my brain went blank for a second. C, 100 less than 500. C, D. Make sure I didn't break any rules again. All right, that's good. Got it. Phew. CD, and then 30. How do I write 30? Well, I can do 3 X's in a row. And 4. How do I write 4? Well, I can't do 4 I's, but I can do 1 less than 5. I, V. Okay? So 434. All right. So the last one I'm expanding. Actually, you guys can do the expanded notation for that one. Let's do the Roman numeral. So let's start. How does it start? It starts with 1,000. Well, 1,000 is easy. 1,000 is M. 900 is tricky. 900 is 100 less than 1,000. So this is 900. 90 is 10 less than 100. 90. And 9 is 1 less than 10. 9. Okay? For 3006, remember when you do expanded notation that if a place value doesn't exist here, you don't have to worry about it. So if I have 3 times 10 to the third plus 6 times 10 to the 0, okay? I don't need the stuff in between. You can write it all. You don't have to. But how do I write this one? This one's pretty straightforward, actually, because I can do 3,000, MMM, and 6. How do I write 6? VI. All right, 1998. It's pretty similar to 1999, right? Because I got 19 and 90. It's just 8 that's different. So I'm going to use that first half. It's MCM 1,990. And then for 8, I can write VIII. That's totally cool. All right, so note the difference between those two. All right. Now we're going the other direction. You have to translate from the Roman numeral to the Hindu-Arabic numeral and expanded form. So take a minute, take a pause. You try it. Okay. All right. Hopefully you tried it all. Here we go. So M is 1,000. I look to its right. There's nothing smaller there. Or sorry, to the left. It just is what it is. So that's 1,000. CM we know is 900 because C is 100 less than 1,000. 9. XC we saw before is 10 less than 100, so that's 90. And I is just a 1. Okay, write it in expanded form. DCL, let's see. Well, D is what? What's D worth? Do you remember? Did you check? D was worth 500. And here's the thing, it's the first thing out there. There's nothing to the left of it. So it's 500. But here's the thing, this is also worth 100. So this is 500 and 100 more, 600. L is worth 50. That's that. All right. Let's see what this one is worth. This is M, there's nothing to its left, so it's just 1,000. CC, there's nothing smaller, it's just a pile of them, so that's 200. Let's see, this is XL, that's 10 less than 50, so that's 40. And then VII, 567, 1,247. Okay, let's do this last one. 10, and then 1 less than 10. So 10, and 1 less than 10 is 9. That's 19. There is one other thing we should do here. So what if I had this? XIX with the bar over it. It would still be 19, but we would be multiplying it times 1,000. So instead of being 19, it would be 19,000. Okay, if I put another bar over it, 19 million, right? Okay. So positional values in base 10 and Hindu-Arabic go 10 to the 0, 10 to the first, 10 to the second, 10 to the third. This is base 10. Positional values in Babylonian go 60 to the 0, 60 to the first, 60 to the second, 60 to the third. This is base 60. We can do math in other bases, okay? What we use to transact our lives, to do money, to count things is base 10. But that doesn't mean it's the only base out there, okay? It's important to note that a place value system for any base has a symbol from each number from 0 to whatever one less than that base is. Think about base 10. In base 10, we use 0 through 9. What this means is that in base 5, our digits are going to be 0 through 4. In base 8, our digits are 0 through 7. In base 2, our digits are 0 and 1, one less than the value of the base. To indicate that a base is being used, you write it as a subscript. So if I want to write 4 in base 8, what I write is 4 subscript 8, 4 base 8. When there is no little number there, if I just write a plain old 4, we assume it's in base 10 because that's the numbers we use, okay? What the other thing we need to talk about, though, is counting in a base, okay? So, like, we know how we count. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we go 11, 12, 13, and so on, right? 14. So this is in base 10. We get 0 through 9. And then we moved to the next place value, the tens place. Well, if I want to count in base, let's say base 5, I only have 0 through 4. So I would go 0, 1, 2, 3, 4. But then I'm out of digits. So when I ran out of digits in base 10, I moved to 10. When I run out of digits in base 5, same thing happens. So now I'm going to go 10, 11, 12. Sorry, my pen and my computer are slow. 13, 14. And now I'm out of digits again. So if we imagined up here, we got to 19. What comes after 19? We ran out of digits. We go to the next value, 20, 10, 11, 12, 13, 14, 20, 21, 22, and so on. Okay, when you get to the end of the values you have, you move up. What if we counted in base 3? We have 0, 1, and 2. Oops, sorry, 0 through 2. So I'd have 0, 1, 2. That's all I got. So I have to move to the next spot. 10, 11, 12. Now what? Well, I ran out again. So 20, 21, 22. And now here's the thing. I can't go to 30. There's no 3, right? So if I really run out, when I get to 99 and base 10, what do I do next? I go to the next place value. It's 100, right? Same thing happens here. So 20, 21, 22, I'm at the end of my place values. It's done. We go to 100. And then we do 101, 102. Same pattern, okay? All right, so that's counting. Now, the real trick in this section is converting bases. So we are going to go both directions, and that's what the additional little video is going to be about converting back and forth. Okay, there are 2 processes here. The first is to go from something in a different base to base 10. So first, look at what you have. I have 324 in base 5, and I want to make it a regular base 10 numbers. First, I have to say to myself, all right, what numbers do I have? 0, 1, 2, 3, 4. Those are my digits. Then I have to think about the positional values for base 5. In base 60, it was 60 to the 0, 60 to the first, 60 to the second. In base 10, it's 10 to the 0, 10 to the first, 10 to the second. In base 5, that's still the case. So my positional values, I lay them out. So it's 5 to the 0, 5 to the 1, 5 squared, 5 cubed, right? And here they are over here. 5 to the 0 is 1. 5 to the first is 5. 5 squared is 25. 5 to the third is 125, okay? Once you have your little chart laid out, then you take your number in that base and put it into the place values. So 4, 2, 3, okay? Then what we do is we combine. So this is 4 1s, 2 5s, 3 25s. 3 25s is 75, 2 5s is 10, 4 1s is 4. Add it together, 89. So 324 in base 5 is worth 89 in base 10. Yes, we're going to do a bunch more of these. Hold on. It's okay. So let's do another one. We don't worry about the pictures base 5 blocks. I think that just makes it harder. But let's start. We're in base 5, so we have 0 through 4. Let's make our chart. 5 to the 0 is the same as 1. I do mine in layers. 5 to the first is the same as 5. Would help if I just actually drew all the lines first. 5 to the second is 25. Okay, so that's our place values. And I just have 3 places here, so that's all I need. And then I'm going to take my number and put it into place. The 2 goes here. The 1 goes here. The 4 goes here. Okay, and now I need to combine. 2 times 1. I have 2 1s. Plus, I have 1 5. Plus, I have 4 25s. Okay, now I just have to calculate. It's 100 plus 5 plus 2. So that means that 412 in base 5 is worth 107 in base 10. All right, you try this one. I know it's weird, it's got an 8. So think first about your place values in base 8. Take a minute, try it yourself. I'm going to make a chart while you're there. And notice I have 4 values, so I'm going to make 4 spots. Okay, make your chart. 8 to the 0 is 1. 8 to the first is 8. 8 squared is 64. 8 to the third is 512. Okay, now put your numbers into place. 4, 3, 7, 2. Okay, and combine. So I have 4 1s. Here I have 3 8s. Here I have 7 64s. And here I have 2 512s. Okay, add up all that together. Interestingly enough, you should get, what number is that? 1500. Okay. There is another one in here in base 2. Base 2 is kind of weird. So stop, pause, try this one. I'm going to make my chart. It's going to take a sec. So let's see. 1, 2, 3, 4, 5, 6. All right, so I have my chart. 2 to the 0 is 1, 2 to the first is 2, 4, 8, 16, 32. Now put your numbers into place. 1, 0, 1, 1, 0, 1. So I have 1, 1. I have no 2s. I'm going to ignore it. I have 1, 4. I have 1, 8. I have no 16s, so I don't care. And I have 1, 32. So 32 plus 8 plus 4 plus 1 gets me to 45. All right, now we're going to do something extra weird. Okay, so this is when we, up until now, we've been using bases smaller than 10, 2, 8, 5, 6, whatever. You can also go the other direction. The most famous example of this is base 12. It's the duodecimal system, technically. You are going to see this in 2 different ways. Sometimes the system uses A and B. Sometimes they make it T and E. Okay. We know that T stands for 10 in our system and E stands for 11, and that's okay, or A and B. So we do it exactly the same way we would. All right. So we make our chart. 12 to the 0, 12 to the first, 12 to the second, 12 to the third. I have 4 place values to deal with. And then I know this is 1, this is 12, this is 144, this is 1728. Okay, so now I'm going to put my stuff into place. It's going to be weird though, okay? So I have a 6, I have a B, I have a 2, and I have a 1. Okay, but here's the thing. I can figure out what to do with this because I have 6 1s. I know looking up here that B is worth 11. That just means that I have B 12s, I have 11 12s. Okay? I have 2 144s. I'm going to give myself enough room, I don't think. Oh, barely. And I have 1 1728. And that's it. Don't let the letters freak you out. Okay, so I converted that over. We add that all up. I get 2,154. Okay, so we can go, in this case, we're going from another base to base 10. This is how we do it. Now we need to go the other direction. This is the last big thing in this section. And then there's one small thing. So to go the other direction, we use division and subtraction. We still need the chart, okay? We still need to know what our positional values are. So I want to take 486, which is in base 10, and turn it into a base 5 number. So I can't just drop the digits in here. That's weird. That's not how it's going to work. What I do is I find the largest place value. So let's see, 125, next would be 625. That's too big. I find the largest place value that I can subtract out of my number, okay? So I have 486. I'm going to subtract away 125 as many times as I can. So I'm going to get 381. Can I do it again? Yes. Okay, I'm going to get 236. Okay, I have more room. I have 125. I'm going to do it again. I'm going to get 111. Okay, so now I don't have enough to take away here 125 again. But how many 125s did I take? I took 1, 2, 3. So in this place value right here, goes a 3. That's how many 125s are in there. And then I'm going to keep going. I'm going to take out 25s. Take out 25. I'm going to bring that up there. Take out 25. Take out 25. Take out 25. And then I'm out of 25s, right? But how many did I use? Well, 1, 2, 3, 4. Okay, and now I can take out 5s. I can take out 5. I can take out 5 again. Okay, so I took out 2 5s. I have 1 left, so I can subtract away 1. So 486 converts to 3,421 in base 5. Okay, now the one thing you should pause and look at before you decide you have an answer is if you have a digit here bigger than something exists in your base, you did something wrong. Like if I had 3,642, there are no 6s in base 5, so I would know something wasn't right. Let's try another. All right, so I want to do 393 into base 5. I know the next number over here would be 625. Okay, so wait, wow, before I do all the work, you do the work. Pause. Try it. Uh-oh. Okay, you tried it, hopefully. So I'm going to do 393, and I can take away 125s. So 268, I have them on the side just to make this a little more efficient. 143. 18. All right, so now I can't take away any more 125s. How many did I take? 1, 2, 3. So I get another 3 here. And now I only have 18 left. So am I going to be able to take out any 25s? No. So that gets a 0. So it's okay. Zeros exist. Minus 5 gets me 13. Minus 5 gets me 8. Minus 5 gets me 3. All right, so how many of those did I take? 1, 2, 3. And then I have 3 left, so I can take out 1 3 times. Now, that means my answer is 3,033 in base 5. Remember that you got to check, okay? 3s exist in base 5, I'm solid. Try another. Let's do 273 and turn it into a base 3 number. Take a minute, take a pause. Try it. Remember the digits you have in base 3 are 0 through 2. Okay, so do your place values first. All right, I'm going to start mine. I don't know how far I'm going to have to go, so I'm going to give myself some space. So that's going to be 1, 3, 9, 27, 81, 243. Yeah, if I go any higher than that, it's too big. Okay, so my first place value is going to start all the way over here at 243. That's the number that's the right size to take out first. Take out the biggest thing you can. You don't want to do extra work. So 273 minus 243 gives me 30. So I can't take out any more of those. I have one of these. I can't take out any 81s. That's a 0. Minus 27 gets me 9. So that's one of those. Oh, gets me 3. It doesn't give me 9. That's a 30. Sorry. Gets me 3. Wait, sorry. I'm going to cribble that out. Bad math. So there are no 9s to take out. I can take out 1 3. And there's no 1s to take out. So my number is 1 0 1 0 1 0 in base 3. Now we're going to do the scary one. We'll do a base 12 one. Okay, in this case, we're going to pretend T is 10 and E is 11. So we're going to convert to base 12. This one is hard. Try it. You got to do all the subtractions. Okay, so think about your place values first. 12 to the 0, 12 to the 1, oops, 12 squared, 12 to the third. I think I end up using 12 to the third as the biggest one. You can check though. Okay, so this is 1, 12, 144, and 1728. And start subtracting. Okay, so as it turns out, you do the work. I'm just going to fill in the numbers because there's not enough possible room on this screen to make that work. So I'm going to take out 3 of these. I can take out 144 10 times. I can take out 12 7 times. And then I can take out 1 5 times. But I know 10 has a value of T. So when I write my number, I'm going to write 3 T 7 5 in base 12. Okay? Crazy, I know. All right. That's one more. And try this one last. Yep, try this one last one. All right, convert this number into base 2. Take a pause, try it. Base 2 is kind of tricky because you have to go pretty far down the path of place values to get to a number big enough to take out of here. Okay? Take a pause, make it work. My final answer here is kind of crazy. It's, let me count them. 1, 2, 3, 4, 5, 6. There's 1, 2, 3, 4, 5, 6. That's the final answer. Okay, so you have to go quite a few place values over here to the left to get a big enough number to start subtracting. And remember, in base 2, all you get are 0 and 1. All right, one last question here. If you look at these numbers, in each case, you have to determine if they are written correctly. So take a second and really look at them and decide, okay? So if we look at 1,203 in base 3, that is not written correctly because there is no 3 in base 3. There's only 0, 1, and 2. If I look at 1206 in base 12, I have a 1, a 2, a 0, a 6. All of those are okay, so that's a yes. 3004 in base 5. In base 5, I have 0 through 4. Those are safe. 3,925 in base 7 is a no-go because I don't have a 9. So that's a no, and that's a no. All right, I'm going to stop this video here. I'm going to do a little additional video. It will be in the same set of notes, just for a side on converting, just so you have an easy reference, and then we're good with this video. So I'll see you in a minute.